The year is 1977, and two spacecraft are sitting on launch pads in Florida, each one about the size of a small car, each one carrying enough instruments to conduct a 5-year scientific mission to Jupiter and Saturn before drifting quietly into obsolescence, somewhere in the outer solar system. That was the plan. That was the complete and entire plan. And for decades, the scientists who built those machines believed they understood, with genuine mathematical confidence, what those spacecraft would find as they traveled outward, how far the sun's influence would reach, what shape that influence would take, and where precisely the solar system would end and interstellar space would begin. They had models, they had equations, they had the accumulated physics of the 20th century behind them. The boundary, they calculated, would be somewhere between 90 and 100 astronomical units from the sun. They were off by 2.4 billion miles, and that was only the first thing they got wrong. The shape they predicted was wrong. The behavior of the magnetic field at the boundary was wrong. And those are not minor calibration errors in an otherwise accurate picture. They are fundamental misreadings of the environment our entire civilization has ever known. By the time Voyager 1 and Voyager 2 finished crossing what their designers never expected them to reach, they had delivered 7 specific discoveries that contradicted the most sophisticated models humanity had produced. Using technology that by today's standards has less computing power than a pocket calculator, still transmitting after nearly 50 years of continuous operation from a distance so far beyond their original destination that the light from their signals takes more than 20 hours to reach the dishes waiting for them on Earth. 7 things the models got wrong. 7 places where the math met reality and reality won. If you enjoy what comes next, consider leaving a like and subscribing. Let's begin. Before we get to what those 7 discoveries were, there is something worth understanding about the machines that made them. Because the instinct, when you hear deep space probe or interplanetary spacecraft, is to imagine something built to the standard of the mission. Something as vast and sophisticated as the distances it was asked to cross. That instinct is wrong. This is the first thing worth understanding about Voyager. Everything it carries is weaker than what you hold in your hand right now. Voyager 2 lifted off on August 20th, 1977. Voyager 1 followed on September 5th of the same year, launched on a faster trajectory despite leaving 2 weeks later, which is why it eventually pulled ahead. Each spacecraft weighs 1,820 pounds, roughly the weight of a large male polar bear or a very small compact car without its engine. Each one stands about 12 feet tall, and across all 3 of the computer systems aboard each spacecraft, the total memory is 68 kilobytes, not megabytes, not gigabytes, 68 kilobytes. The photograph you took on your phone this morning almost certainly weighs more in digital terms than the entire computational storage aboard a spacecraft currently traveling in interstellar space. A single second of compressed audio on a modern streaming service consumes more memory than Voyager uses to navigate, communicate, and operate its instruments simultaneously. The phone sitting in a drawer somewhere in your house that you no longer use, the one with the cracked screen that you keep meaning to recycle, carries millions of times more memory than the machines we sent to the edge of the solar system. That is not an approximation. That is a measurement. The power situation is no less striking. At launch, Voyager's radioisotope thermoelectric generators produced 470 watts of electricity, roughly the output of 4 or 5 incandescent light bulbs burning at once. Nearly 50 years later, that number has decayed considerably. But the transmitter, the piece of the spacecraft responsible for shouting its findings across billions of miles of space, operates at 23 watts. A standard LED bulb in a reading lamp uses between 8 and 12 watts. Your kitchen refrigerator cycles through more power than Voyager uses to send its signal across the entire solar system. And by the time that signal arrives at the large dish antennas on Earth, after traveling at the speed of light for 22 hours from Voyager 1's current position, or 18 hours from Voyager 2's, it has spread and weakened across such an incomprehensible volume of space that the received power is approximately 1 quintillionth of a watt, 1 quintillionth. If you wanted to charge a modern smartphone battery using that signal, and nothing but that signal, you would need to collect it continuously for several 100 million years before you had accumulated enough energy to power a single charge cycle. That is the signal we are working with. That is the voice, reaching back across all that distance. And yet these machines were sent on an extraordinary mission, made possible by a celestial alignment so rare that it will not repeat for another 176 years. In the late 1970s, Jupiter, Saturn, Uranus, and Neptune were arranged in a configuration that allowed a spacecraft to slingshot from one planet to the next using gravitational assists, each giant world accelerating the probe and bending its trajectory toward the next target without burning additional fuel. The window was narrow and the mathematics were demanding, but the opportunity was genuine, and NASA took it. What drove those spacecraft outward, and what scientists needed to understand before they could predict where the solar system ended, was the solar wind. The sun does not sit quietly in space. It continuously sheds material in every direction, a constant outflow of charged particles, mostly protons and electrons, streaming away from the solar corona at speeds between 250 and 500 kilometers per second. To put that in terms the body can process, the fastest human-made object before the Voyager probes themselves reached perhaps 10 kilometers per second under rocket power. The solar wind moves at 25 to 50 times that speed without any assistance. It moves at a significant fraction of the speed of sound within the plasma itself, which travels at 30 to 60 kilometers per second, meaning the solar wind is decidedly supersonic by that measure. And the sun loses approximately 1 million tons of mass to this wind every single second. Not every day, not every hour, every second. 1 million tons of material leaves the sun and spreads outward in all directions, continuously, like a slow-motion explosion that has been running for 4.5 billion years. This wind does not travel forever. Eventually, it collides with the interstellar medium, the extremely thin gas and dust that fills the space between stars. And thin is an almost absurdly inadequate word here. The interstellar medium in our region of the galaxy contains approximately 1/10 of an atom per cubic centimeter. 1/10. The air in the room around you contains roughly 10 to the 19th atoms per cubic centimeter. That is a 10 followed by 19 zeros. The interstellar medium is so empty that if you compress the distance between the atoms in that room down to human scale, the interstellar medium would look like a single grain of sand distributed across a volume the size of the Earth. The solar system is moving through this near vacuum at 137 kilometers per second, about 490,000 miles per hour. And as it moves, the solar wind presses outward against the interstellar medium on the leading side and stretches behind on the trailing side, forming a shape roughly like a comet or a teardrop, with a compressed nose pushed forward and a long tail streaming behind. The physics is precisely what happens when a boat moves through still water and presses a bow wave ahead of itself. The interstellar medium is the water. The heliosphere is the boat, the place where the solar wind finally runs out of momentum, where it slows, piles up, and becomes turbulent before the interstellar medium takes over, is called the heliopause, and by the 1980s and 90s, scientists had built detailed computer models predicting where it would be. The physics was well understood. The solar wind speeds were measured. The pressure of the interstellar medium was estimated. The math was solid, the models were sophisticated, and the consensus pointed clearly to a boundary somewhere between 90 and 100 astronomical units from the sun. 1 astronomical unit is 93 million miles. The distance from the Earth to the Sun, 90 to 100 of those, that translated to roughly 8.4 to 9.3 billion miles from home. The models agreed. The equations held. The scientists were confident. Keep this in mind as we explore what they found, because what comes next shocked every scientist who studied the data. Voyager 1 reached that predicted zone on December 16th. 2004 crossing the termination shock at 94 astronomical units from the Sun, 8.7 billion miles from home. That number sat comfortably inside the range the models had forecast, and for a brief moment, it must have felt like confirmation. 27 years of travel through the outer solar system, and the boundary appeared almost exactly where the equations said it would. The models had placed it between 90 and 100 astronomical units. 94 was close enough to feel like a triumph, but that is not quite the full story of what Voyager 1 found. 2 years before that confirmed crossing, on August 1st, 2002, Voyager 1's instruments detected what looked like the termination shock. The particle counts shifted. The magnetic field readings changed. Every signature pointed to the same conclusion. The boundary was right there, at approximately 85 astronomical units, and Voyager had just passed through it. The scientists watching the data understood what they were seeing. And then, over the following weeks and months, the signatures reversed. The particle counts shifted back. The solar wind around Voyager 1 became supersonic again. The boundary had not stayed where it was. It had moved, pushed outward by a pulse in the solar wind, retreating past the spacecraft, leaving Voyager stranded back inside the region it thought it had already exited. Voyager 1 had crossed the termination shock, and then the termination shock had crossed back over Voyager 1. The boundary was not a fixed wall. It had moved through the spacecraft. This is the first thing the models got catastrophically wrong, and it is worth sitting with what it actually means. The scientific community had spent decades treating the heliopause and termination shock as stable structures, objects with addresses, boundaries you could write down as a number of astronomical units and file away. The solar wind blows outward, the interstellar medium pushes back, equilibrium is reached, and the boundary forms at a predictable distance. That is the model. That is what the equations produced. The truth is almost precisely the opposite of static. The boundary breathes. When solar activity increases, when the sun throws off a particularly intense burst of wind, the heliosphere expands outward, pushing the termination shock further from the sun. When activity decreases and the wind pressure drops, the interstellar medium pushes back inward and the boundary contracts. It moves, continuously, over millions of miles, expanding and compressing like a lung responding to its own changing pressure, and nothing in the original models had adequately captured that behavior. The boundary did not have an address. It had a range, and that range shifted with the sun's mood in ways the equations had significantly underestimated. Voyager 2 confirmed this in a different way. When it crossed the termination shock on August 30th, 2007, it did so at 84 astronomical units, 7.8 billion miles from the sun. Voyager 1 had crossed at 94 astronomical units. The two spacecraft crossed the same boundary at the same type of location, both traveling roughly outward from the sun, and yet there was a 10 astronomical unit difference between their crossing points. 10 astronomical units. That is 930 million miles, roughly the distance from the sun all the way out to Saturn. The same boundary, crossed by two spacecraft in the same general neighborhood of the heliosphere, separated by a gap wide enough to swallow the inner solar system and most of the outer solar system behind it. That gap is not measurement error. That gap is the boundary being in genuinely different places at different times, responding to solar activity that had changed in the years between the two crossings. The termination shock had contracted inward by close to 1 billion miles between 2004 and 2007. Sit with the geometry of that for a moment. A boundary that can move nearly 1 billion miles over the course of a few years is not behaving like a wall. It is behaving like a membrane stretched over a living thing, and the living thing is the sun, exhaling and inhaling on timescales that make the entire heliosphere flex in ways that the models had treated as negligible. The models assumed a kind of steady state. A solar wind blowing at a consistent average pressure against an interstellar medium of consistent average density, producing a boundary at a consistent average location. What Voyager found was that the averages are real, but the variations around those averages are enormous, and those variations matter enormously to anything trying to navigate or describe the boundary from the outside. And this was only the first surprise. Both Voyagers had now crossed the termination shock and entered the heliosheath, the turbulent outer layer between the shock and the true edge of the sun's influence. The models describe this region as a transitional zone, somewhat chaotic, but ultimately traversable in a relatively predictable way, leading to a clean crossing into interstellar space. The scientists expected that the hard part was behind them. The heliosheath was supposed to be the difficult middle, the turbulent no man's land between the termination shock and the true edge of the sun's domain, and both Voyagers were now inside it, pushing outward through plasma that the models described as disordered, but ultimately manageable. The instruments were still running, the data was still coming back, and the scientists watching that data believed, reasonably, that they understood the broad shape of what would happen next. The solar wind particles would gradually thin out as the spacecraft approached the heliopause, the true boundary where the sun's influence ends entirely. Cosmic rays from interstellar space, which the heliosphere normally deflects, would gradually increase. The magnetic field carried by the solar wind would rotate, reorienting itself to align with the interstellar magnetic field on the other side. And then, over a period of weeks, or perhaps a few months, the transition would complete and Voyager would be unambiguously outside. That was the model's prediction. That was what the equations described. And every prediction was wrong. What Voyager 1 detected instead, beginning in the summer of 2012, was something that had no clean name in the existing models and no analog in anything the instruments had been designed to find. In June of 2012, as the spacecraft was moving through the outer heliosheath, at distances no human object had ever reached, the instruments recorded a sudden and dramatic change. Solar particles, the low-energy charged particles carried outward by the solar wind, dropped sharply, close to zero. Simultaneously, galactic cosmic rays, the high-energy particles streaming in from interstellar space, surged to levels that the team had expected to see only after a clean heliopause crossing. Those two signals together, every researcher on the team knew, were the fingerprints of the crossing they had been waiting for. The solar system was letting go. Interstellar space was filling in. By every particle measurement available to them, Voyager 1 had crossed. But the magnetic field hadn't changed direction. And that was a problem, because the magnetic field was supposed to be the definitive test. The sun's magnetic field and the interstellar magnetic field are oriented differently, and crossing the heliopause should produce a clear, measurable rotation in the field direction Voyager recorded. A kind of compass needle swinging to point at a new north when you cross from one domain into the other. That rotation never came. The particle data said one thing. The magnetic data said something incompatible. And the team found themselves in a genuinely strange situation, holding two sets of readings that should not have been able to coexist, trying to understand what the boundary had actually done to the spacecraft and whether the spacecraft had actually crossed it. What they eventually determined was that Voyager 1 had entered a region they had not predicted and did not yet have a framework to describe. A region where the magnetic field lines from inside the heliosphere and the magnetic field lines from interstellar space had connected, threading through the boundary like threads through a needle, creating channels along which particles could move freely between the two domains without the spacecraft itself having fully crossed. The field lines were running parallel, acting as lanes that linked the heliosheath to interstellar space, and charged particles were streaming along those lanes in both directions simultaneously. Scientists came to call this the magnetic highway, not as a formal designation, but as a description of the physical behavior they were watching in the data, and it was something that none of the models had anticipated. The models had drawn the heliopause as a surface, a membrane where one set of conditions stopped and another began, and what Voyager found was not a membrane. It was a region of interpenetration, a zone where the two environments were woven together through their magnetic geometries in a way that made clean categorization impossible. Think about what that geometry actually means for the shape of the boundary you are trying to cross. The simplest version of the heliosphere, the version most people carry in their minds, is a sphere, a bubble with the sun at the center and a well-defined wall at the edge. That image is wrong in at least two important ways, and the magnetic highway pointed toward both of them. The heliosphere is not a sphere. Because the solar system is moving through the interstellar medium at 137 kilometers per second, the leading edge of the heliosphere gets compressed by the oncoming interstellar gas and dust, while the trailing edge stretches out behind, drawn into a long tail by the momentum of everything flowing through it. The shape is closer to a bullet or a teardrop, blunt at the front and drawn out at the back, and the boundary conditions on the compressed leading edge are fundamentally different from the boundary conditions in the stretched tail. Voyager 1 and Voyager 2 were not crossing identical versions of the same boundary. They were crossing different regions of an asymmetric structure at different times through field geometries that varied enormously from one location to another, and the magnetic highway was evidence of how complicated those geometries could become at the actual crossing point. This is not a metaphor. This is a measurement. Voyager 1 officially crossed the heliopause on August 25th, 2012, at a distance of 121 astronomical units from the Sun, 11.2 billion miles. The scientists argued about that date for months after the fact, working backward through the data to identify the moment when the magnetic field finally rotated and the interstellar medium's conditions became unmistakable. Voyager 2 followed on November 5th, 2018, at 119 astronomical units. Slightly closer, for the same structural reasons that caused the termination shock asymmetry years earlier. The original models had placed the heliopause somewhere between 90 and 100 astronomical units. The actual crossing was 2.4 billion miles farther out than the most confident predictions. A distance larger than the gap between the Earth and the Sun repeated 25 times over. And it was not a clean crossing. It was the end of a months-long transition through a region that behaved nothing like a wall, and nothing like a simple membrane. It behaved like a coastline. Not a coastline as you might picture it on a map, a clean line separating land from water, but a coastline in the way geographers actually measure coastlines, where the finer the resolution of your ruler, the more complex and fractured and recursive the shape becomes, where every apparent boundary contains smaller boundaries within it, and the total length of the edge depends entirely on what scale you choose to examine it. The solar system's edge is that kind of boundary, not a place you cross so much as a gradient you move through, with pockets of solar influence extending further than expected in some directions, and interstellar conditions reaching deeper than expected in others, with magnetic geometries connecting the two regions in ways that make the categories themselves imprecise. The honest answer is we still do not know the full shape of our own heliosphere. After nearly 50 years of operation and 2 spacecraft making the crossing, the shape remains genuinely uncertain. The tail structure remains unresolved, and the models that describe what lies beyond the edge are about to meet the same fate as every model that came before them. Solar particles have vanished from Voyager 1's instruments. Cosmic ray counts have stabilized at their interstellar levels, but what those instruments are now measuring in the space beyond the heliopause is not what anyone built the equations to predict. The explanation, when it finally arrived, did not feel like a triumph. It felt like the universe had simply refused to cooperate in the most arbitrary way imaginable. The reason Voyager 1's magnetic field did not rotate when it crossed the heliopause, the reason the compass needle stubbornly kept pointing in the same direction even as everything else around it changed, was not because the models had the physics wrong, and it was not because Voyager 1 had failed to cross. It was because the galactic magnetic field in that particular region of space, at that particular location where the heliosphere happens to end, is aligned almost exactly parallel to the Sun's own magnetic field. The two fields happen to point in roughly the same direction by coincidence. Not by design, not by some deeper structural principle, not because of any underlying symmetry that the physicists had missed. The galactic field and the solar field just happened, in that small corner of the Milky Way, to share the same orientation. Sit with that for a moment. The galactic magnetic field just happened to point the same direction as the Sun's. What this means is that when Voyager 1 passed through the most carefully anticipated boundary in the history of space exploration, the one diagnostic scientists had treated as the definitive test of the crossing, the magnetic field rotation, was simply unavailable, not because nothing was happening, but because of the specific geometry of the interstellar neighborhood the Sun happens to occupy. The solar system drifts through a region of the galaxy where the large-scale magnetic field runs almost parallel to the local field of the heliosphere. And that coincidence, that piece of pure cosmic indifference, made years of observational data nearly uninterpretable. Voyager 2 confirmed the crossing the way scientists had originally expected. When it crossed the heliopause in November of 2018, its instruments detected a 20-degree rotation in the magnetic field, a real, measurable swing in orientation, which retrospectively validated the physics and confirmed that Voyager 1 had indeed crossed the boundary back in 2012, but had simply done so through a region where the diagnostic was invisible. This is not an elegant resolution. This is the universe placing a random obstacle exactly where you were trying to measure something, through no mechanism other than geometry and chance. And then the instruments sent back readings from the other side, and the story got stranger still. The interstellar medium that Voyager 1 had spent decades approaching turned out to be almost nothing. Not nothing in the colloquial sense, not empty in the way people speak about vacuum as a vague absence of substance, but measured, quantified, instrument confirmed, almost nothing. The density of the space beyond the heliopause is approximately 0.08 particles per cubic centimeter. That is fewer than 1 particle per cubic centimeter of space, on average, across the interstellar medium through which the solar system drifts. The best laboratories on Earth, using equipment specifically engineered to evacuate chambers to the lowest achievable pressures, have never come close to producing a vacuum this complete. A cubic centimeter of the room around you contains roughly 10 million trillion particles. A cubic centimeter of interstellar space contains roughly 1/10 of a single particle. The interstellar medium is approximately 10 trillion times less dense than the air you are currently breathing, and even that comparison does not fully convey how thoroughly empty it is, because 10 trillion is not a number that the human mind has any real foothold on. It is a 1 followed by 25 zeros. You could take every breath drawn by every human being who has ever lived and spread those molecules across the distances Voyager now travels and still not approach the density of what surrounds it. And yet, that almost nothing is hot. The temperature of the interstellar medium runs between roughly 54,000 and 90,000 degrees Fahrenheit. Those are measurements from Voyager's instruments, and they are correct. And they are also completely misleading in the way that temperature often is at these scales. Temperature, in the strict physical sense, measures the average kinetic energy of particles. How fast the individual particles in a region are moving, how much energy they carry. In interstellar space, the particles move very fast. Their individual energies are high. But because those particles are separated by enormous distances from one another, the total thermal energy present in any given volume is almost immeasurably small. An astronaut exposed to interstellar space without a suit would not burn. The particles moving at temperatures of 60 or 70,000 degrees are so rare that the astronaut's body would encounter almost none of them. The astronaut would freeze and quickly, because the near-perfect vacuum would conduct no heat at all while the body radiated its warmth into the surrounding emptiness. The pressure confirms this. Pressure in the interstellar medium measures at approximately 0.000000003 pascals. Standing at sea level on Earth, the atmospheric pressure on your body is approximately 101,000 pascals. The pressure of interstellar space is about 110 trillion times less than that. If you tried to build a container capable of maintaining interstellar pressure conditions, and you stood next to it, the force differential across its walls would be essentially the entirety of Earth's atmospheric pressure on one side, and a number so small, It has no practical analogue in terrestrial experience on the other. The models had predicted a warmer medium. They had predicted a denser medium. They had predicted pressure readings within comprehensible ranges. Interstellar space, the space that Voyager 1 became the first human-made object to enter, turned out to be emptier, colder in its real thermal effect, and at a lower pressure than the equations had built in. Every measurement contradicted the expectation, and Voyager's instruments were still running, still transmitting, still finding new things to contradict. Because from deep within that near-perfect vacuum, the spacecraft had begun detecting something that no model had predicted at all. A wave propagating outward through the interstellar medium from its source inside the heliosphere, carrying with it the pressure of events that had happened millions of miles away and months before the wave arrived. That wave was not a coincidence. It was not a random fluctuation in the interstellar medium throwing up an anomalous reading that Voyager 1 happened to pass through. It was the direct, measurable consequence of something that had happened inside the heliosphere. A solar outburst, a coronal mass ejection, the sun releasing 1 billion tons of plasma at millions of miles per hour in a single violent exhalation. And that event, which had occurred months earlier and millions of miles behind Voyager, had travelled outward through the heliosphere, struck the heliopause like a hammer coming down on a drumskin, and launched a shockwave into the interstellar medium that propagated outward at roughly 60 kilometers per second. 60 kilometers per second sounds fast, and by any terrestrial standard it is. A commercial airliner crosses the continental United States in about 5 hours. 60 kilometers per second would do it in under 2 minutes. But the interstellar medium is not measured in continental widths. The distances through which these waves propagate are measured in astronomical units, in billions of miles, and at 60 kilometers per second, a wave still takes months to reach Voyager's position and years to travel any meaningful fraction of the space surrounding our solar system. And yet, it reaches. The sun's violence does not stop at its own boundary. It punches through, carries across, and continues into the medium that was supposed to be beyond its reach. Voyager 1 detected one of these waves in October and November of 2012, which was, not coincidentally, almost immediately after the spacecraft had crossed the heliopause in August of that same year. The wave arrived, the plasma density jumped, the instruments recorded it, and then, in April and May of 2013, another wave arrived, and in March of 2014, another, and again in 2015. Each wave traced back to a solar event, each one demonstrating that the boundary between the heliosphere and interstellar space is not the final chapter of the sun's story, but merely a transition. A place where the sun's direct wind ends, but its percussion continues, propagating outward through the void for years after the events that generated it. This is the fifth thing the models did not anticipate. The heliosphere was understood to be a shield, and it is, but a shield that transmits force, that carries the sun's outbursts forward into the medium beyond its walls, and continues delivering those outbursts long after the solar wind itself has been stopped. And this matters in ways that extend beyond the elegant strangeness of the measurement, because the interstellar medium through which those waves travel is not uniformly empty. It has structure. It has a magnetic field, the galactic magnetic field, which is ancient and vast and almost impossibly weak by any familiar standard. That field measures at roughly 50 nanoteslas. Earth's magnetic field at the surface measures approximately 50,000 nanoteslas. The galactic field is 1/1,000,000th the strength of the field that deflects your compass needle. You could not detect it with any instrument you hold in your hand. It is, by every intuitive measure, negligible. And yet it is not negligible at all, because charged particles respond to magnetic fields regardless of how weak those fields are, provided the particles have far enough to travel and the field extends far enough to act on them. A field of 50 nanoteslas, extending across hundreds of light years, exerts cumulative influence on cosmic rays. The high-energy particles streaming through the galaxy from supernova remnants, from pulsars, from sources so distant and so energetic they are still not fully catalogued. Those particles do not travel in straight lines through the galaxy. They curve, they are guided, and the direction they arrive from, when Voyager's instruments detect them, is not the direction the models predicted. This is the 6th and 7th discovery folded into each other, because they are related. The magnetic field orientation in our local interstellar neighborhood turned out to be angled differently than the models assumed, and as a consequence, cosmic rays arrive at Voyager from preferred directions, from angles that suggest the field lines in our local bubble are channeling them in ways that nobody had fully anticipated. Think of field lines not as invisible barriers, but as channels, like grooves pressed into the fabric of space, and cosmic rays as particles that prefer to travel along those grooves rather than across them. If the grooves run one way, the particles arrive from one direction. If they run another way, the particles arrive from somewhere else. What Voyager detected was that the grooves run in a direction that the models had not correctly predicted, which means our entire local neighborhood, the small region of the galaxy that contains our solar system, the heliosphere, and the bubble of interstellar medium immediately surrounding it, has structure that we were not mapping correctly. There are features out there, magnetic features, density features, structural features in the interstellar medium that deflect incoming radiation and shape what reaches us. And we did not know they were oriented the way they are until an instrument launched nearly 50 years ago drifted into position to measure them. And the implication of that extends backward through time in a way that is genuinely unsettling. The heliosphere's shape changes. It breathes. It compresses and expands. Over geological timescales, as the solar system moves through different regions of the galaxy, the heliosphere passes through denser and less dense patches of interstellar medium, and as it does, it shrinks and grows, exposing the inner solar system to more or less cosmic ray flux. What reaches Earth, what has always reached Earth, has been shaped by structures in the interstellar medium that we are only now beginning to locate. The cosmic ray environment of the early Cambrian was not the same as the one today, and neither was shaped purely by the sun's output. It was shaped by where we were, and what was out there, and how the field lines were running in the neighborhood we happened to be passing through. 7 discoveries. 7 things the models did not expect. And all of them measured by 2 spacecraft that were never designed to go this far, transmitting on 23 watts of power across distances that light itself takes 16 hours to cross. So the question that follows from that is the one that has been waiting since the beginning. How did they get there? The answer to that question begins not at the edge, but at the center, or close enough to it. In 1977, the engineers at the Jet Propulsion Laboratory had identified something that would not happen again for 176 years. A geometric alignment of the outer planets so favorable that a single spacecraft, launched at precisely the right moment, could visit Jupiter, then use Jupiter's gravity to slingshot towards Saturn, and from Saturn onward, gaining speed at each encounter rather than spending fuel to achieve it. This technique is called a gravity assist, and it sounds simple when you describe it in a sentence. But the calculations required to thread a spacecraft through those windows, to arrive at the right position relative to a planet measured in the billions of miles, with enough precision to bend the trajectory exactly as needed, represented some of the most demanding applied mathematics of the 20th century. The planets do not sit still. They are moving. The spacecraft is moving. The gravity field of each planet is a 3-dimensional well, and you have to approach that well from the correct angle, at the correct velocity, so that the planet's gravity accelerates you toward the next destination, rather than pulling you off course entirely. Getting that right, in the 1970s, using computers that fit inside a box and processed information at speeds that would seem laughable beside the phone sitting in the room you're in right now, was not a routine achievement. So both Voyagers launched in the late summer and early fall of 1977, and the first world that rewrote everything was Jupiter. Voyager 1 reached Jupiter in March of 1979, and Voyager 2 arrived that July, and what they found there did not match what people expected from a distance. Jupiter rotates in under 10 hours, which for a planet large enough to swallow 1,000 Earths is a figure that takes a moment to absorb. The surface of that planet is completing a full rotation faster than a long intercontinental flight. And the result is atmospheric winds measured at 400 miles per hour. Sustained. A continuous, not the remnant of some storm, but the permanent condition of the atmosphere. The Great Red Spot, which observers have been watching from Earth for centuries, rose 5 miles above the surrounding cloud layers, a storm larger than our entire planet, elevated above its neighbours by the sheer persistence of its own circulation. And it had been running continuously for longer than recorded human history. But Jupiter itself was not the discovery that landed hardest. The discovery was on its moons. Jupiter has 4 large moons: Io, Europa, Ganymede, and Callisto, and the scientific consensus before Voyager arrived was that these were cold, geologically dead worlds, frozen relics of the early solar system. Everything we thought we knew about these worlds was a sketch drawn from a distance. Voyager showed us the painting. When Voyager 1's cameras resolved Io with enough detail to study its surface, a navigation engineer named Linda Morabito noticed, while processing images to locate stars for position calibration, that something was erupting. A plume, rising 200 miles above the surface of Io, moving at roughly 1,000 miles per hour, arcing up and outward in a shape that could only mean one thing. This moon, this small rocky body in the outer solar system, was volcanically active. Not in the geological past. Right then. While the spacecraft was flying past, Io was erupting. Over the course of both flybys, 9 active volcanoes were confirmed, and later missions would catalogue over 400 of them, making Io the most volcanically active body in the entire solar system, by a margin that is not close. And the question that followed immediately was why? Earth has volcanic activity because it retains internal heat from its own formation and from the decay of radioactive elements deep within its mantle, a slow, diffuse process spread across the whole planet. Io is not large enough to hold that kind of internal heat on its own. Something else was happening. The answer turned out to be Jupiter's gravity itself. Io orbits so close to Jupiter, and in a resonance with the other large moons, that Jupiter's tidal forces continuously stretch and compress Io as it moves through its orbit, kneading the moon the way your hands might work clay, and the friction from that constant deformation generates heat, not in a thin layer but throughout the interior. Enough heat to sustain continuous volcanic eruptions on a scale that dwarfs anything on Earth. Tidal heating. The mechanism was not new in principle, but nobody had seen it operating at this scale, and finding it active, present, and visually spectacular on a world that was supposed to be geologically inert was the kind of discovery that does not just add a fact to the record, it adds a mechanism, a category of planetary behavior that had to be incorporated into every subsequent model of how worlds work. And then there was Europa. Europa's surface, when Voyager's cameras resolved it, was almost featureless by planetary standards. Smooth ice, with a network of long fractures running across it, very few craters, which in planetary geology means the surface is young, which means something is resurfacing it, which means there is process, there is activity, there is heat moving through the interior. The same tidal forces acting on Io were acting on Europa, and the smooth fractured ice was telling a specific story. Beneath that shell, there was very likely liquid water. Not frozen. Liquid. An ocean, insulated from the cold of space above by the ice layer, and heated from below by tidal forces in the rock beneath it. That ocean, if it exists, and the evidence has only strengthened since Voyager, would be in contact with a rocky seafloor. And everywhere on Earth where liquid water contacts rock with a source of chemical energy, there is life. Europa became, in the years following Voyager's flyby, one of the most compelling targets in the search for life beyond Earth. Not because anyone had found life there, but because the conditions that allow life had been found there, unexpectedly, on a moon that had not been considered a serious candidate until these fragile machines, built with 1970s technology, flew past and resolved it clearly enough to read what its surface was saying. Jupiter alone, one planet among the several Voyager would visit, had rewritten the science of volcanism, of tidal heating, of ocean formation, and of where in the solar system life might be possible. Saturn's rings were about to reveal their own secrets, and Titan's atmosphere would change the trajectory of Voyager 1 forever. Saturn was not supposed to be different. After everything Jupiter had revealed, the volcanic violence of Io, the hidden ocean beneath Europa's ice, the sheer scale of a system that had turned every prior assumption inside out, there might have been a temptation to approach the next planet with recalibrated humility, to expect the unexpected. But Saturn's rings, even in the pre-Voyager imagination, felt like something already understood. Billions of particles, yes, but particles governed by orbital mechanics, by gravity, by laws that had been written down and tested and trusted for centuries. The rings were beautiful, certainly, but they were not supposed to be mysterious. And then Voyager's cameras came close enough to actually resolve them. The rings of Saturn, seen at distance through a telescope, appear as a continuous disk, smooth and uniform, the kind of thing you might sketch in a single stroke. What Voyager saw was nothing like that. The rings are composed of countless individual particles, chunks of ice and rock ranging from grains of dust to boulders the size of a house, each one following its own orbital path around Saturn, and the structure that emerges from all those individual motions is not smooth at all. It is layered and divided and rippled with gaps and waves and density variations that the pre-Voyager models had not predicted with anything close to the precision required. There were ringlets within ringlets. There were gaps maintained not by simple absence of material, but by the gravitational influence of small moons shepherding particles into lanes. A mechanism that had been theorized but never observed in action at this scale. And watching it operate in real data was a different thing entirely from having written down the equations. The rings stretch outward for hundreds of thousands of miles from the planet's surface, which sounds like a vast, deep structure. And yet, if you were to scale Saturn down to the size of a beach ball, the rings would be thinner than a single sheet of paper. Not roughly as thin. Thinner. A structure that spans distances, which would dwarf the distance from Earth to the Moon, reduced in its vertical dimension to something you could destroy by drawing a finger across it. That is not a poetic comparison. That is a measurement of the actual geometry, and the geometry means that the rings exist in a plane so precise, so flat relative to their own diameter, that the orbital mechanics maintaining that precision had to be actively managed by gravitational forces working continuously across billions of individual objects. The models had predicted rings. They had not predicted this kind of structure, this kind of precision, this kind of complexity embedded in something that had seemed, from Earth distance, like a simple disk. And then there was Titan. Titan, Saturn's largest moon, was known to have some kind of atmosphere. That much had been detected from Earth. What Voyager 1 found when it arrived was an atmosphere so thick, so opaque, so dense with organic haze that the surface was completely invisible. Not partially obscured, completely hidden behind a shroud of orange-brown nitrogen and complex organic molecules. A chemistry that is not a thin veneer, but a deep, a layered system of nitrogen and methane cycling through processes that, at Titan's surface temperature of negative 290 degrees Fahrenheit, are not metaphorically similar to Earth's water cycle. They are structurally analogous to it, with methane playing the role that water plays here, forming clouds, raining down, pooling on a surface that no camera had ever seen. Voyager 1 flew within 2,500 miles of Titan's surface, closer than any other target in the Saturn system, and still could not see through that atmosphere to the terrain below. What it could measure was the chemistry, the density, the layered structure of a world whose surface conditions were so unlike anything in the existing catalogue that scientists needed years to fully process what they had collected. That close approach, 2,500 miles, was not a scientific luxury. It was a choice. To pass that close to Titan, Voyager 1's trajectory was bent by the moon's gravity into a path that sent the spacecraft up and out of the plane of the solar system entirely, away from the orbital plane where Uranus and Neptune waited. Voyager 1 would never visit those planets. The decision to study Titan deeply was the decision to end the grand tour for that spacecraft. It was a permanent sacrifice, made because what Titan had turned out to be was too important to pass at a greater distance. So Voyager 2 carried the mission forward alone to the outer planets, and what it found there continued the pattern that had been established at every stop along the way. Uranus was supposed to be a cold, quiet ice giant, distant and relatively featureless. Its axis of rotation is tilted 98 degrees from the vertical, not tilted like Earth, which leans at a modest 23 degrees and produces the gentle progression of seasons, but tilted so severely that Uranus essentially rolls along its orbit on its side, like a barrel rolling down a slope rather than a top spinning in place. The consequence of that tilt is that each pole receives 42 years of continuous sunlight, followed by 42 years of complete darkness, a cycle so extreme that the planet's atmosphere had been expected to behave in dramatic, asymmetric ways as a result. It did not. The atmosphere was, surprisingly, relatively uniform despite the extreme seasonal imbalance, which was itself a puzzle, not a confirmation of the models, but another deviation that required explanation. And Uranus's small moon, Miranda, a fractured, geologically chaotic body that appeared to have been shattered and reassembled at some point in its history, carried on its surface a cliff face called Verona Rupes that rises approximately 6 miles from its base to its top. 6 miles of vertical drop. The Grand Canyon, one of the deepest surface features on Earth, descends roughly 1 mile from rim to floor. Verona Rupes is roughly 6 times that, rising from a landscape that should, by any prior reasoning, have been cold and inactive and geologically dead for billions of years. Neptune, the final planet, carried winds of 1,300 miles per hour. Sustained, atmospheric winds, not gusts, not transient disturbances, but the permanent condition of an atmosphere at the edge of the solar system where temperatures drop to levels that should suppress the energy driving any weather system at all. And Triton, Neptune's largest moon, vented nitrogen geysers from its surface at a temperature of negative 391 degrees Fahrenheit, the coldest measured surface temperature of any object the spacecraft had visited. And still, something beneath that surface was warm enough, pressurized enough, to drive material upward through the ice and into the thin sky above. Every planet, every major moon encountered in detail, every stop along the Grand Tour had produced discoveries that the prior models had not predicted, had not contained, had not even framed as questions worth asking. The gentle reframe that imposes itself here is not that science had failed. The models were approximations built from limited data, and approximations built from limited data will always miss the details that only close observation can reveal. But the pattern matters, because the same models, the same frameworks, the same confidence that had been applied to the planets were now being applied to the edge of the solar system. The models had worked well enough for gross predictions. They had gotten Voyager to Jupiter, to Saturn, to Uranus and Neptune. What they had not done at any single stop along the way was correctly predict what would actually be found there. And a planet stays where you put it. A planet has a fixed location, a fixed mass, a fixed gravity where you can calculate and verify and refine. The edge of the solar system is not like that. The edge of the solar system moves. So the question that imposes itself, after all of that, after every planet, every moon, every atmosphere that refused to behave the way the models said it should, is what comes next. Not for the solar system, but for the 2 spacecraft that spent decades threading through it. Because there is a version of this story that feels like conquest. Voyager crossed the boundary. It passed through the termination shock, through the heliosheath, through the heliopause itself, and entered the space between the stars. The instruments are still running. The signal is still arriving. And if you were constructing a narrative about human achievement, you might end it there, with the quiet satisfaction of knowing that something we built, something that weighs less than a compact car and runs on a power budget smaller than a string of porch lights, has now crossed into interstellar space. And that would be accurate, as far as it goes. But accuracy and completeness are not the same thing. The space Voyager has entered is not empty in the uniform way that the old models once assumed. The Sun, along with the entire solar system, is moving through the galaxy at roughly 137 kilometers per second. And at the moment, that journey happens to be carrying us through a particular region of the interstellar medium called the local interstellar cloud. A loose, warm region of gas and plasma that has been partially shaping the heliosphere's structure for thousands of years. The heliosphere we measured with Voyager, the one that turned out to be so much smaller and stranger than predicted, exists partly as a function of the pressure this cloud exerts against the sun's outward wind. But the sun will not remain inside this cloud indefinitely. Current estimates suggest we will drift out of it within the next few thousand years. And when that happens, the heliosphere will change shape again. The boundary that Voyager crossed, the one that required decades of measurement and generated 7 major wrong predictions, is not a permanent fixture. It is a response to a local condition that is itself temporary. The mission even carries a formal acknowledgement of this new phase. The Voyager Interstellar Mission, the name NASA assigned once the primary planetary objectives were complete. A recognition that the spacecraft had moved into a different category of exploration entirely. The name sounds expansive, and then you look at the numbers. Voyager 1 is currently approximately 159 astronomical units from Earth. That translates to roughly 14.8 billion miles. 14.8 billion miles is a distance that takes the signal from Earth 22 hours to cross even traveling at the speed of light. And it is the farthest any human-made object has ever traveled. And every prediction was wrong about the planets, about the edge, about what waited past the boundary. And so perhaps it should not be surprising that the instinct to feel that 14.8 billion miles represents something close to interstellar arrival is also wrong. Because the nearest star to our own sun, Proxima Centauri, sits at a distance of 4.24 light-years. That number deserves careful treatment. 1 light-year is the distance light covers in a full year, traveling at roughly 6 trillion miles per year. 4.24 light-years is approximately 25 trillion miles. 25 trillion miles compared to the 14.8 billion miles Voyager has already covered. If you imagine the distance Voyager has traveled as a single inch on a map, 1 inch representing that entire 14.8 billion miles of flight time, that entire 50-year journey, then Proxima Centauri would sit approximately 140 feet away, across the room and down the hall and out the door. The inch is real. The 140 feet is what remains. Voyager 1 is traveling at approximately 38,000 miles per hour. That is faster than any human-made object has ever traveled relative to the sun. Faster than the rockets that carried people to the moon. Faster than any probe we have since launched. 38,000 miles per hour sounds, in the context of human engineering, like an extraordinary achievement. At that speed, you could cross the continental United States in about 5 minutes. At that speed, you could circle Earth's equator in roughly 40 minutes. And at that speed, traveling continuously, without slowing, without stopping, it would take Voyager approximately 73,000 years to reach Proxima Centauri. 73,000 years. Let that number settle. Recorded human history, the written record, the cuneiform tablets, the earliest agricultural societies, the first cities rising in Mesopotamia, extends back approximately 5,000 years. 73,000 years is roughly 14 times longer than that entire documented span of human civilization. Agriculture itself, the practice of deliberately planting crops and managing land, began somewhere around 10,000 to 12,000 years ago, when the last major ice age was retreating and glaciers were pulling back from the northern continents. Voyager, at its current speed, would need 6 or 7 times the entire period since the ice age ended just to reach the nearest star. Not to explore the nearest star's system, not to orbit it, not to study whatever planets might circle it. Simply to arrive in its vicinity. The Ice Age ended. Civilizations rose and fell and rose again. Writing was invented. Mathematics was invented. The printing press was invented. The steam engine was invented. The airplane was invented. The rocket was invented. And Voyager was built and launched. And still it would need all of that time again, multiplied many times over, just to close the distance to the single closest point of light in the sky. There is a small additional detail that clarifies how vast this emptiness actually is. In approximately 40,000 years, Voyager 1 will pass within about 1.6 light-years of a star called Gliese 445, a dim red dwarf in the constellation Camelopardalis. 1.6 light-years is not a visit. It is not even a close approach in any meaningful sense. It is a drift past a point in space that happens to have a star somewhere in the general direction, at a distance that would itself take thousands of additional years to cross. Voyager will not enter that star's system. It will not encounter its gravity in any significant way. It will pass through the surrounding emptiness at an angle, continuing onward into space that contains nothing in particular, and the star will simply be a slightly brighter object in its cameras. If those cameras were still working, which they will not be, the power will have been gone for tens of thousands of years before that moment arrives. So, the picture that assembles itself is this: the farthest traveling object humanity has ever built, moving faster than anything we have ever launched, has crossed the edge of our sun's influence, and it is still, by every meaningful measure of interstellar distance, essentially here. The voyage from shore to open ocean is complete, and the open ocean turns out to be something that no ship we can currently imagine was built to cross. So the natural question, the one that tends to arrive at this point in the thinking, is whether speed could simply solve the problem. If Voyager moves too slowly, then build something faster. If 73,000 years is unacceptably long, then find a way to shorten it. The reasoning feels sound. It feels like the kind of engineering challenge that human history has a reasonable track record of overcoming. And so it is worth following that reasoning all the way to where it actually leads, because the destination is not encouraging. To reach Proxima Centauri within a single human lifetime, within roughly 80 years of travel, a spacecraft would need to cover 4.24 light-years in that window. Working backward through the arithmetic, that requires traveling at approximately 10% of the speed of light. 10% sounds modest when framed that way, as though there is 90% of potential remaining. But 10% of the speed of light is 67 million miles per hour. To give that number some physical grounding, consider that Voyager 1, the fastest traveling object humanity has ever built, moves at roughly 38,000 miles per hour. 67 million miles per hour is approximately 1,760 times faster than that. If Voyager's speed were a single step, the speed required for a human lifetime journey to the nearest star would be nearly 2 miles, not a longer stride, a categorically different kind of motion. And this is where the interstellar medium, that thin, cold, almost empty space that Voyager spent decades crossing and measuring, becomes the central problem. Because at low speeds, the interstellar medium is genuinely close to nothing. 0.08 particles per cubic centimeter sounds like an absence, and in practical terms, at the speeds of any object we have ever launched, it essentially is one. Voyager moves through it without incident, without erosion, without meaningful resistance. The particles are so sparse and the speed so low that the medium barely registers as matter at all. At 67 million miles per hour, the same medium becomes something else entirely. Kinetic energy scales with the square of velocity. This is not a minor detail. It means that if you double your speed, the energy carried by each collision does not double. It quadruples. If you multiply your speed by 1,000, the energy per collision increases by 1,000,000. At 10% of the speed of light, a single hydrogen atom, one proton, essentially invisible, carrying almost no mass, arrives at the hull of a spacecraft with approximately 6 electron volts of kinetic energy. 6 electron volts does not sound threatening in isolation. It is a number that sounds like it belongs on the label of a small battery. But consider that a spacecraft with a cross-section of just 1 square meter, moving at that speed through interstellar space, would be struck by roughly 100 trillion hydrogen atoms every single second. 100 trillion collisions per second, each delivering 6 electron volts, accumulating continuously, without pause, across years or decades of travel. The total energy deposited into the hull generates thousands of watts of heat, concentrated in the forward-facing surface of the spacecraft, the same surface that must remain structurally intact for the entire duration of the journey. Sit with the arithmetic for a moment. Thousands of watts of continuous heat, arriving not from an engine or a power source that can be managed and regulated, but from the medium itself, from the supposedly empty space the spacecraft is moving through. The void Voyager measured, the one that seems so sparse and cold and inert, becomes a sandstorm at relativistic speeds, not metaphorically. The energy load is real, it is continuous, and it does not diminish as you travel farther from the sun. The interstellar medium extends all the way to the destination, and the heat is only part of it. The same collisions that deposit thermal energy also generate radiation damage, because high-velocity particle impacts do not simply warm a material. They displace atoms within the crystalline structure of whatever the hull is made of, creating defects that accumulate over time. Materials that begin a journey ductile and structurally sound gradually become brittle under sustained radiation bombardment. The molecular architecture of the hull breaks down not in any single catastrophic event, but through thousands of trillions of small displacements, each individually negligible, collectively lethal to the integrity of the structure. A spacecraft that launched with a perfect hull would, over years of travel at 10% of the speed of light, be developing microfractures and material weaknesses at every forward-facing surface, with no means of repair and no way to stop the process. The universe does not forbid interstellar travel. It simply prices it beyond anything we can currently afford. And the price is not set arbitrarily or by some engineering limitation that patience and ingenuity might eventually overcome. It is set by the physical laws that govern how energy behaves at high velocities. Laws that apply universally and do not contain exceptions for sufficiently motivated civilizations. What makes this particularly striking is that the danger is not coming from something dense or dramatic. It is coming from the same thinly scattered medium that Voyager spent decades drifting through in complete safety. The emptiness itself is the hazard, and the hazard scales in a way that makes it worse the faster you go, not linearly, but as the square of your speed, climbing rapidly toward values that no known material can survive indefinitely. And even setting aside the physics of the interstellar medium, any spacecraft leaving the inner solar system would first need to cross something that is not yet fully mapped and not yet fully understood. A vast outer structure whose edges may extend far beyond where Voyager has reached, and which represents the sun's last, most distant gravitational claim on anything moving through space. And that vast outer structure is the Oort cloud, a region that most people have heard named but few have genuinely reckoned with in terms of its actual dimensions. The common understanding of the solar system places its boundaries somewhere around the heliopause, the edge Voyager 1 crossed in 2012 at roughly 121 astronomical units from the Sun. That is already an enormous distance, 11.2 billion miles, a span that takes light more than 16 hours to cross. But the heliopause is not where the Sun's influence ends, not even close. The Oort cloud, the vast reservoir of icy bodies that surrounds the solar system in a nearly spherical shell, extends from roughly 2,000 astronomical units out to nearly 100,000 astronomical units from the Sun. 100,000. The heliopause sits at 121, which means the Sun's gravitational reach extends nearly 1,000 times farther than the boundary Voyager crossed after 35 years of travel. Sit with that ratio for a moment. Everything Voyager 1 accomplished in 35 years of continuous flight, every milestone, every shock, every particle count, every boundary crossed, brought it to roughly 0.1% of the distance to the outer edge of the Oort cloud. The solar system, in its true gravitational sense, is not the tidy arrangement of planets and rings that ends somewhere beyond Neptune. It is something almost incomprehensibly larger, a structure so immense that Voyager 1, the fastest object humanity has ever launched into deep space, has barely entered its outermost territories after nearly 5 decades of travel. To cross the Oort cloud at Voyager's current speed would take approximately 30,000 years. Not 30,000 years to reach the other side of the galaxy. Not 30,000 years to cross some gulf between star systems. 30,000 years to exit the region where the sun still holds gravitational sway over wandering objects. Where comets are still loosely bound to this star, still falling inward on orbits so long and slow that they will not complete a single circuit in the lifetime of human civilization. The agricultural revolution that allowed the first settled cities to form happened roughly 10,000 to 12,000 years ago. The span of time required to cross the Oort cloud is 2 to 3 times the entire age of farming on Earth. When Voyager 1 finally emerges from the outer boundary of the Oort cloud, if its trajectory carries it through the densest part of the shell, modern humans will not exist in any form that would recognize the probe or remember sending it. The sun refuses to let go, and it refuses across distances that make the heliopause, the boundary we spent decades predicting and years celebrating, look like a doorstep. This is the context in which the probe's mortality becomes something to sit with carefully. Because those instruments, that 1970s technology built and launched when personal computers did not yet exist, and the word gigabyte had no practical meaning, that technology is running out of time. Each Voyager carries a set of radioisotope thermoelectric generators, devices that convert the heat released by the radioactive decay of plutonium-238 into electrical power. At launch, in 1977, those generators produced approximately 470 watts, enough to run 4 or 5 modest light bulbs, enough to power a small household appliance. And with that, humanity communicated across billions of miles for decades. But plutonium-238 decays at a steady, inexorable rate, losing roughly 4 watts of output every single year. By 2026, both probes will be generating approximately 249 watts. The threshold for basic operations, keeping the instruments running, maintaining the transmitters, sustaining the heaters that protect the electronics from temperatures cold enough to destroy them, sits at approximately 245 watts. That is a margin of 4 watts. The difference between a functioning scientific instrument at the edge of the solar system and a silent frozen machine drifting in the dark is less than the power drawn by a single strand of old-fashioned Christmas tree lights. 4 watts. And that margin is narrowing by 4 watts every year, which means it is not really a margin at all. It is a countdown, and the engineers at the Jet Propulsion Laboratory know exactly what the numbers say. The decisions being made right now are among the most quietly consequential in the history of space exploration. Engineers must choose which instruments to shut down first, which heaters to sacrifice, which systems to let grow cold in order to preserve the ones that still have something to tell us. In 2020, mission controllers shut off the cosmic ray heater on Voyager 2, a small device designed to keep the cosmic ray instrument's detector assembly warm enough to function reliably. At the time of shutdown, the temperature around that instrument dropped to negative 74 degrees Fahrenheit. That is cold enough to crack certain plastics, cold enough to cause lubricants to solidify, cold enough that no one was certain the instrument would keep working. And yet it did. The detector continued returning data, functioning below its rated temperature range, operating in conditions it was never designed to survive, which is perhaps the most fitting summary of what these probes have always done. That 1970s technology, assembled by human hands on workbenches in California, has outlasted every expectation by margins that make the word durable feel insufficient. But durability has limits, and 4 watts per year has no sentiment about them. By 2030, possibly 2032, the power will fall below the minimum threshold that cannot be worked around. The transmitters will lose their ability to hold a coherent signal. The instruments will begin to freeze. One by one, the voices will go quiet, and the Oort cloud will swallow whatever signals remain before they can cross the distance to reach us. And after that silence, the probes will continue, drifting forward at 38,000 miles per hour, carrying no power and no voice, but carrying something else entirely. Something that was never meant for any scientist on Earth. Something else entirely. Before the transmitters go quiet, before the instruments freeze, before the probes become nothing more than metal and memory moving through the dark at 38,000 miles per hour, each one carries a disk. Not a data module in the scientific sense, not a backup drive for the mission's findings. Something far more deliberate than that. Assembled not by engineers optimizing for efficiency, but by a group of people asking a question that has no engineering answer. If something out there ever finds this, what should it know about us? Each probe carries a 12-inch copper disc plated in gold. The gold is not decorative. Gold is chemically inert, resistant to corrosion in ways that almost no other material can match over the timescales being considered. Not decades, not centuries, but millions of years of drifting through interstellar space. The disk was built to last. That is the first thing to understand about it. Every choice in its construction reflects the assumption that it might survive longer than the civilization that built it. Encoded on that disk, as audio signals, waveforms pressed physically into the surface the way a vinyl record stores music, are 116 images. Not photographs in any format that requires modern technology to interpret, but images converted into audio frequency signals with instructions for how to decode them printed on the cover. Someone receiving this object would hear the images before they could see them, and the cover tells them how to reconstruct the pictures from the sound. 116 of them, photographs of human anatomy, of cells under a microscope, of ocean waves and mountain ranges and city streets, and a woman nursing an infant, and a man eating a meal, and children at play, and the page of a book. Not a highlights reel, not propaganda. An attempt at honest representation, assembled by a committee of scientists, artists, and thinkers who argued at length over what to include and what to leave out, understanding that every choice was a statement about what we believe matters. Alongside the images, 55 greetings spoken aloud in 55 different languages, ranging from ancient Sumerian to modern Mandarin, from English to Amoy to Wu. Each one a brief, spoken welcome. Hello from Earth, in forms recognizable to almost every linguistic tradition humanity has produced. The idea being that if whoever finds this speaks none of those languages, the sheer variety of sounds and rhythms might itself communicate something. That this species had many voices, many ways of encoding meaning in sound. That language itself is one of the things that defines us. And there is music. Johann Sebastian Bach's Brandenburg Concerto No. 2, performing a kind of mathematical precision so clean that it sometimes strikes scientists as the most universal thing humanity has ever produced. Ludwig van Beethoven's String Quartet No. 13, carrying the full weight of what a single human mind could assemble from vibration and silence. Senegalese percussion rhythms that the Western ear might struggle to follow, but that communicate a physical intelligence about rhythm and pattern that transcends any particular tradition. Pygmy music from the Central African rainforest, recorded as part of an honest attempt to represent not just the civilizations that happened to build the spacecraft, but the full breadth of what human cultures have made with sound. A Georgian polyphonic choir, whose harmonic structure sounds almost entirely unlike anything produced in the Western tradition. The selections were not random, and they were not made quickly. Every piece was chosen to demonstrate something irreducible about what humans do with time and vibration. The cover of the disc carries instructions for playing it. Because of course it does. Because the disc is useless without them. The playing speed is engraved, 16 2/3 rotations per minute, expressed in a way that does not require a shared language to decode, using the spin of a hydrogen atom as a universal unit of time that any technologically advanced civilization would recognize. The cover also includes a diagram of a human hand raising in greeting, a diagram of the solar system, and a map that is perhaps the single most extraordinary element of the entire object. Etched onto the cover are 14 lines radiating outward from a central point, each line a different length, each corresponding to a known pulsar, a rotating neutron star that emits a beam of radiation at a precise and unique frequency. Essentially, a lighthouse in the galaxy that pulses at a rate so specific that no two are alike. Pulsars slowly change their rotation speeds over time, and those rates are well understood, which means that any civilization advanced enough to receive this disk would be able to use the 14 pulsars as a cosmic address, locating the source of the disk not just in space but in time. Knowing which pulsars are represented, knowing their frequencies, knowing how those frequencies are changing, a receiver could work backwards and determine not only roughly where in the galaxy this object came from, but roughly when it was launched. This is not a metaphor. This is a measurement. It is like giving your home address using the positions of lighthouses visible from anywhere on a vast ocean. Except the ocean is the Milky Way, and the lighthouses are already burning across thousands of light years. Sit with the deliberateness of that for a moment. Someone in 1977 sat down and encoded the location of the civilization that built the disk using the physics of neutron stars, trusting that a sufficiently advanced finder would have the tools to read it. They were not sending a postcard. They were building a key, a self-contained, self-explaining artifact designed to be understood without any prior contact, any shared history, any common frame of reference. They were committing to the idea that the laws of physics are the same everywhere, and that those shared laws are the only language we have. And then they attached this object to a spacecraft and threw it into an ocean so vast that the probe will travel for 73,000 years and still not reach the nearest star. The golden record will almost certainly never be found. The universe is too large, the probe too small, and the silence between stars is so complete that the odds of any intersection with another intelligence approach zero in any time frame that could be called meaningful. The people who built it knew this. Carl Sagan, who oversaw the record's creation, understood precisely the arithmetic involved, and they made it anyway. Assembled it with extraordinary care, debated every selection, encoded the pulsar map with the precision of people who believed it mattered. Not because they expected it to be received, but because the act of deciding what represents us, the images, the greetings, the music, the address written in the language of neutron stars, was itself the point. The record is not the footnote to the mission. The science ended and the record continues, and what it carries into the dark, past the heliopause and through the interstellar medium, and eventually into the silence between stars, is the question of what was worth saving. What the record actually carries, though, is harder to hold than the engineering of it. It is easy to admire the pulsar map, the encoded images, the precisely calculated playback speed. These feel like problems solved, like acts of intellect applied to an enormous challenge. But set those aside for a moment and listen to what else they put on the disc. Because the people who built it understood something about the question they were trying to answer that the engineering alone does not capture. They recorded a baby crying. Not a symbolic sound, not a stand-in for birth or life or the continuity of generations in any abstract sense. An actual infant, crying the way infants cry because they are overwhelmed by the newness of existing. They recorded human footsteps, the specific rhythmic percussion of a body moving across the earth that we have been making for 100,000 years. They recorded laughter, male laughter, female laughter, the involuntary sound a human body makes when something exceeds expectation in the direction of joy. They recorded a heartbeat, which is the oldest sound any of us knows, because we all spent our first 9 months hearing it through the walls of another body. And they recorded the sound of a kiss between a mother and her child, a baby crying, a heartbeat. the sound of a kiss between a mother and child. These are the sounds we chose to represent all of us. Not our governments, not our wars, not our architecture, not our mathematics. Though some of those made the record too. But these particular intimate sounds, the textures of being alive in a human body, the sounds that pass between people in rooms where no one is performing for anyone, and then the music. Bach's Brandenburg Concerto No. 2, which is a piece so architecturally precise and emotionally inexhaustible that musicians have spent 300 years returning to it and not using it up. Beethoven's String Quartet No. 13, which is late Beethoven, written when he was almost entirely deaf, when the music existed first and only in his imagination before it existed anywhere else. Senegalese percussion, which carries a rhythmic intelligence utterly unlike the Western tradition, a way of organizing time into sound that developed completely separately and arrived at something equally true. Pygmy songs from Central Africa, polyphonic and layered in a way that sounds like many voices agreeing on something that cannot be said in words. A Georgian polyphonic choir, voices braided together in a harmony so old it predates the formal theory of harmony by centuries. Each of these was someone's answer to the question of what an alien civilization would need to hear in order to understand something real about the species that built the spacecraft. And the answers are all different, and they are all human, and taken together they do not sound like a dataset. They sound like a civilization trying, in the best way it knows how, to say something true. And the chance that any other ear will ever hear any of it is essentially zero. This is the weight that sits underneath all of it, and it is important to let it land rather than move past it quickly. Think of a message in a bottle, the old romantic image of a note tucked inside glass and thrown from a shore, trusting the currents to carry it to someone. Now imagine that the ocean receiving that bottle is not the Atlantic or the Pacific, but the entire galaxy. 100,000 light years across, containing 400 billion stars, and most of them separated from each other by distances that even Voyager 1, the fastest object humanity has ever launched, would require tens of thousands of years to cross between any two. The bottle is the size of a large kitchen appliance. The ocean is 100,000 light years in every direction. There may be other shores out there. We genuinely do not know. But even if there are, even if intelligences exist around other stars capable of building instruments, reading pulsar maps, decoding the spin transition of hydrogen atoms, the likelihood of any of them intercepting an object this small, moving through space this vast, over any time scale that could be called reasonable, is so small that calling it a long shot would be a profound understatement. The record will drift. The two spacecraft will drift with it. Through the interstellar medium, through whatever structure lies beyond, onward into a silence so complete and so permanent that the concept of retrieval becomes almost philosophical. The people who made it knew this. Carl Sagan knew it when he oversaw every selection, every encoded image, every greeting recorded in each of 55 languages from Sumerian to Mandarin. They knew the arithmetic. They knew what the distances meant. And they stayed up late anyway, arguing about which photograph of a human being captured something essential, debating whether Chuck Berry and Blind Willie Johnson deserved inclusion alongside Bach and Beethoven and the Senegalese drummers, agonizing over whether the world they were representing on 12 inches of gold-plated copper was honest or flattering or true. They made it with care that the universe will almost certainly never acknowledge. But perhaps that was never the point. And the more you sit with the golden record, with the years of argument and selection and care that went into it, the more clearly that becomes true. The golden record was never really meant for aliens. It was meant for us. Because think about what the act of making it actually required. Carl Sagan and his collaborators could not simply grab a hard drive and copy over everything humanity had ever produced. They had to decide. They had to look at the entire expanse of human experience, every culture, every language, every musical tradition, every image of a river or a spine or a nursing mother, and ask, which of this is essential? Which of this, if it were all you had, would let you understand what kind of creature made these objects and launched them into the dark? That question sounds like it has a clean answer until you try to answer it. And then it becomes one of the most difficult philosophical projects a person can undertake. They were not curating a museum exhibit. They were deciding, under genuine pressure, what humanity is. And they had to do it by looking at themselves from the outside, the way an alien would have to look, with no shared history, no common language, no assumption of similarity. They had to imagine a perspective from which everything familiar about being human was strange, and then build something that would survive that strangeness and still communicate something real. That is not a scientific task. That is a deeply human one. And the record they produced is, among other things, a document of that attempt, a record of a species trying to name its own most essential qualities, and finding, in the process, that the naming itself was worthwhile. The chance that any intelligence will ever find it is essentially zero. We established that. The math of interstellar distances and the physical size of two spacecraft drifting through the enormous emptiness between stars makes retrieval not just unlikely, but effectively impossible on any timescale we can meaningfully imagine. But there is something in that fact that is not tragic. Or at least, not only tragic. Because the people who decided which music deserved to represent humanity already received the answer. The choosing was the gift. The people who argued late into the night about whether a particular photograph of a human hand was honest or flattering, they learned something in that argument about what they valued and why. The 55 individuals who leaned into a microphone and said hello in languages ranging from Sumerian to Mandarin were, in that moment, holding the whole weight of their language's history and placing it gently into a copper disc as an offering to nothing certain. And that act changed them. These things happened. They are part of the record of what humanity did with its knowledge when it finally reached far enough to look back. And on February 14th, 1990, it looked back in the most literal way possible. Voyager 1 was roughly 3.7 billion miles from Earth, farther than any camera had ever pointed back at home, and mission controllers sent a command. The spacecraft rotated. 60 frames of imaging were taken across the solar system, and in one of them, caught in a scattered band of sunlight from the camera's optics, there was Earth. Not a sphere, not a disk, not a recognizable shape of any kind. A fraction of a pixel. The image was later described as a mote of dust suspended in a sunbeam, and that description is not poetic embellishment. It is a precise physical account of what the image contains. Earth, from 3.7 billion miles, does not look like a planet. It looks like an artifact of light. It looks like something you might dismiss as a camera imperfection if you did not already know to look for it. Now understand what that fraction of a pixel contains. Every mountain range that has ever been climbed is on that dot. Every ocean crossed by every vessel since the first human being lashed wood together and pushed out from a shore is on that dot. Every city ever built, every library ever burned, every field ever planted, every child ever born is on that dot. The entirety of recorded human history, the 5,000 years of writing and agriculture and warfare and music and philosophy and science that produced, among other things, the spacecraft taking this photograph. All of it happened on a fraction of a pixel, caught in a band of scattered light at the edge of the solar system. That is not a compression of scale for rhetorical effect. That is where we actually live, rendered at a distance that is, in cosmic terms, still essentially local. 3.7 billion miles is still inside our own solar system. From the position Voyager 1 occupies now, at roughly 159 times the distance between the Earth and the Sun, the Earth does not appear in any photograph at all. It is not a fraction of a pixel. It is nothing. The instruments are not capable of resolving it. The sunlight that faintly illuminated that mote of dust in 1990 has been diluted across another 11 billion miles of space, and what was already barely visible has become invisible entirely. And this is where the Voyager story becomes something larger than science, because the spacecraft are not stopping. They have no means of stopping. They will drift past the boundary of interstellar space, which they have already crossed, and continue into the galaxy at 38,000 miles per hour, which sounds like speed until you measure it against the distances ahead. In 30,000 years, they will still be inside the Oort cloud. In 73,000 years, Voyager 1 will pass within roughly 1.6 light-years of a dim star called Gliese 445, and no human eye will be there to see it. Because by that point, it is genuinely uncertain whether humanity will still exist in any recognizable form. The probes were built to last years. They have lasted nearly 50. But the galaxy they are drifting into operates on timescales that dwarf not just the mission, but the species that launched it. They may outlive us entirely. Two small machines carrying gold-plated copper records of music and greetings and photographs, drifting silently through a darkness in which no one is listening, speaking for a civilization that may no longer exist to be spoken for. And yet, this is the part that requires sitting with, because it runs against every instinct we have about what a mission like this is supposed to mean. The wrongness was the point. Not a regrettable footnote to the achievement. Not an embarrassing asterisk. The wrongness was the discovery. Consider what the Voyager program actually cost, from the moment of launch through the Neptune encounter in 1989. $865 million. That number sounds enormous until you hold it against what it purchased. Many single commercial buildings in major cities cost more than that now. A professional sports stadium routinely exceeds $1 billion, $865 million across more than a decade of flight, across Jupiter and its impossible volcanic moon, and its ocean-covered moon, and its 400-mile-per-hour winds, across Saturn, and its rings so thin that a scaled model the size of a beach ball would have rings thinner than a sheet of paper, across Uranus tilted on its side, across Neptune and its impossible retrograde moon venting nitrogen into the dark, across two boundary crossings into interstellar space, across every particle count and magnetic field measurement and plasma wave detection that rewrote our models of what lies beyond the heliosphere, across all of that. The bill was less than the cost of keeping a professional football franchise running for 3 seasons. That is what the most scientifically productive robotic mission in human history cost. And the returns were not what anyone expected, because almost everything discovered was a surprise, and surprise is the only honest unit of scientific progress. Go back through what Voyager actually found. Io, which should have been a dead, cratered rock, turned out to be the most volcanically active body in the solar system, with plumes rising 200 miles at nearly 1,000 miles per hour. 9 volcanoes confirmed in the initial data, more than 400 identified afterward. Europa, which should have been unremarkable ice, turned out to be smooth in a way that implied something moving beneath the surface. Something liquid. Something kept warm by tidal forces from Jupiter's gravity. A candidate for life so serious that it now drives the design of entire future missions. Saturn's rings, expected to be simple and relatively uniform, resolved into thousands of distinct bands with gaps and waves and braided structures that no model had anticipated. Uranus was tilted so far onto its side that its poles experienced 42 years of continuous sunlight, followed by 42 years of continuous darkness, an axial behavior so extreme that the word tilted barely captures it. Miranda, a moon of Uranus, carries a cliff face roughly 6 miles tall, 6 times the depth of the Grand Canyon, on a moon small enough to walk across in a matter of days. Neptune's winds reached 1,300 miles per hour, which is not a weather event but a permanent atmospheric condition on a world that receives almost no solar energy to drive it. Triton orbits its planet backward and breathes nitrogen geysers into space at temperatures near 400 degrees below zero. 7 wrong predictions. 7 times the universe opened a door and something wholly unexpected walked out. The heliopause was not where the models said it would be, not the shape the models described, not bordered by the magnetic field orientation the models assumed. The termination shock crossed by Voyager 1 and Voyager 2 differed by 10 astronomical units, 930 million miles. A discrepancy the models had no room for. The interstellar medium turned out to be hotter than expected, more complex than expected. A fabric of plasma and magnetic field that pushed back in ways that surprised every physicist who had spent years predicting it. And every prediction was wrong, not as a humiliation. As an education, the kind that only costs $865 million and 50 years of patient listening. This is, in fact, exactly what science does. Lewis and Clark did not return from the Missouri River with a completed map. They returned with a rough sketch that raised more questions than it answered, and what made their journey matter was not the accuracy of what they found, but the fact that they went and looked. Magellan's expedition did not prove the Earth was round. That was already known. It proved that the Pacific was larger than anyone had conceived, that the world was less compact and more dangerous than the charts suggested. Apollo did not conquer the moon. It revealed that the moon was geologically complex in ways no telescope could show, and it brought back samples that took decades to fully interpret. Progress in exploration is not a straight line from ignorance to mastery. It is a jagged climb through successive layers of wrongness, each layer more sophisticated than the last. Each revision more precise than the one it replaced. And this is what the Voyagers are, ultimately. Not a triumph in the sense of conquest, a triumph in the sense of honest inquiry. Built in the 1970s, assembled with technology that fits in the palm of your hand today, I launched on a trajectory that depended on a planetary alignment that will not repeat for another 176 years, kept alive by engineering margins measured in single watts. These two machines, drifting now at 159 and 132 astronomical units from a star they can no longer illuminate, have spent 5 decades demonstrating that the universe is larger, stranger, and less cooperative with human models than anyone believed. And the data is still coming. Weak, ancient, 22 hours old by the time it arrives, received on dishes the width of a small arena, but still arriving. Still correcting us. There are plans, still theoretical, for an interstellar probe that could reach 500 to 1,000 astronomical units, traveling at speeds between 80,000 and 160,000 miles per hour, roughly 4 times Voyager's pace. If launched in the 2030s, it might reach its target range sometime in the 2080s. The people who would analyze that data are, in many cases, not yet born. This is what the Voyager mission made possible and necessary. The understanding that the questions are multi-generational, that no single human lifetime is long enough to send something to interstellar space and receive a complete answer. That we are not doing science for ourselves, but for whoever comes after, carrying forward a process of patient wrongness and careful correction that has no foreseeable end and no final chapter. And so, here is where we end up. After all of it, after the termination shock and the heliopause, after the magnetic field that bent the wrong way, and the pressure boundary that breathed and shifted like something alive, after the plasma waves and the golden record and the pale blue pixel suspended in a shaft of scattered light, here is what remains when the measurements are filed and the instruments have gone quiet. 2 machines are out there right now, drifting through the local interstellar medium, carrying a 12-inch gold-plated copper disc that holds a baby crying and a heartbeat, and a mother kissing a child, and a piece of Bach written 300 years before anyone imagined leaving this planet. They are not slowing down. There is nothing in the interstellar void to slow them. They will travel outward for millions of years. Long after the sun has expanded and consumed the inner planets, long after whatever we have built on this world has dissolved completely, long after every language spoken into those 55 greetings has been forgotten, and the civilizations that invented them have passed entirely out of memory, the Voyagers will still be moving, not toward anything, not guided, just moving, because nothing will stop them. The chance of anyone finding them is essentially zero. This is still true. It was always true. But somewhere in the long process of sitting with that fact, something shifts. Because the people who designed the golden record knew it was essentially zero. They encoded it anyway. They chose to press a mother's kiss into gold and throw it into the dark, knowing, with full mathematical clarity, that the gesture was almost certainly permanent and private and unreturned. And they did it anyway, because the act of reaching was the point, not the arrival, not the reply. The reaching itself, the decision to extend a hand into a void that cannot hold it and will not answer. This is what a mote of dust floating in a sunbeam does not do. It drifts. It follows the light. It does not turn itself upward and ask where the light is coming from or how large the room is or what lies beyond the window. We are vanishingly small. We live in a temporary pressure bubble, less than a fraction of a percent of the distance to the edge of our own solar cloud. On a world that registers as a fraction of a single pixel when viewed from a distance, we ourselves created. The 3-pound organ floating in the center of your skull, running on roughly 20 watts of electrochemical power, is what measured all of that, is what built the instruments, solved the equations, calculated the trajectory, waited 50 years for a signal thinner than a whisper, and understood what it meant. That is not a comfort offered to soften the scale. That is a measurement, the same as any other, and it is the one that matters most. The opening of this story was always the same. A pair of machines, each weighing about as much as a large motorcycle, flung outward on a trajectory made possible by a planetary alignment that comes once every 176 years, carrying a transmitter drawing less power than the bulb over a reading chair. Everything that followed was the universe answering back in ways we did not predict, correcting us, revising us, showing us a boundary more complex and strange than any model we had prepared. We were wrong about almost everything. The shape was wrong. The temperature was wrong. The pressure was wrong. The magnetic field was wrong. And in being wrong, we learned the actual shape of the room we live in, which is a thing we could never have known without going to look. The Voyagers will outlive us. They will outlive everything we have ever made or named or loved. And somewhere in the dark between stars, a gold disc will be traveling with a heartbeat pressed into it. And the heartbeat will belong to no one anymore. And it will still be moving. Still carrying that particular human sound outward through a silence so complete that the sound itself becomes an argument, not for our importance, not for our permanence, but for the simple and unrepeatable fact that we were here, and we noticed, and we wanted whoever came after to know that we had looked up, tried to understand what we were looking at, and found it beautiful. That is where we leave the Voyagers, not lost, not forgotten, moving,